good morning. You remember that we had derived equation of motion, that is Navier-Stokes equations, and we had given you a problem. Not we had given you, we had given the problem and solved also, right. We said that the Navier-Stokes equations are so useful that in many cases they are used, and used in the sense you see that there is a velocity term, there is a viscosity term, so shear stress term, all these wherever it was required or it is required, you can use them. And you remember we had solved the problem like this, that a cylinder, two coaxial cylinders, right, two coaxial cylinders, one is like that and another was like this, they were there and a fluid within this is there, and we said that inner cylinder, this is the inner cylinder, is rotating, no, is fixed, and the outer cylinder is rotating, outer cylinder is rotating with an angular velocity of omega, right. And we said the velocity profile is like this v theta, right. This is the velocity profile. So, for this we had done the solution, right. Now, if the same problem, if we say in a different way, in the problem remains explicitly same, the language wise, that if an incompressible fluid is flowing between two vertical coaxial cylinders and the outer one is rotating with an angular velocity of omega, determine the velocity for the tangential laminar flow. So, there is no change in the language, no change in the problem. Only if we were asked now that if you remember, we had said that this was R and this was KR, right. That was our problem given earlier. Now, if we do the same problem like this, right, if we do the same problem like this, right, where you see here instead of R at the boundary, at the inner one and KR at the outer one, if we just interchange that KR is in the inner one and R is in the outer one, right. So, we say now that we have these two coaxial cylinders, right, and the radii are like this, this is KR and this is R, right. All other remains same, that velocity profile is like this v theta, right. Here we are saying that outer cylinder is rotating with an angular velocity of omega, inner cylinder is fixed, right. So, the same problem just changed the radii. Then if you remember what was our earlier solution, that let me show you first. Our earlier solution was like this: V theta was omega k square into r square minus r square divided by 1 minus k square into r. This was our earlier solution, that is under this situation this was our solution, right. Now, we have changed, we have said only all other things remain same, only we are changing the radii, inner radii and outer radii. So, we made inner radii kr and outer radii r, right. In this case, outer radii was a multiple of k which is more than 1. In this case, inner radii is a multiple of k r rather which is less than 1, right, because in this case as it is appearing r is greater than k r, in this case it is appearing r is less than k r. So, it is multiple of k r where the constant is greater than r or 1, rather in this case it is less than 1, right. All other things remain same. If this be the case, then let us see how we can proceed, right. You see, we have started here with that from the given problem V r is equals to V z is equals to 0, del V theta del theta is 0, same. From Navier-Stokes equation we got the first equation rho V theta square by r is equal to minus del P del r minus rho V theta square r is equals to minus del P del r. This was from the first equation. From the second equation we got 0 is equals to del del r of 1 by r del del r of r V theta. This was from the second equation, and from the third equation we got 0 is equals to minus del P del z plus rho g z. So, all these three equations remain identical. So, we can write from the physical understanding of the given problem, we can write V r is equals to V z is equals to 0 and del V theta del theta is equals to 0. It is a steady laminar and incompressible fluid, right. This was our given. So, these two remain same. So, then from the Navier-Stokes equations we can write number 1 equation minus rho V theta square by r is equals to minus of del P del r, right. Then we also can write that second equation we can write 0 is equal to del del r of 1 by r of del del r of r V theta, right, 2, 3, right. And third one, from the Navier-Stokes equation we can write 0 is equals to minus del P del z plus rho g z, right. So, obviously that this is r and this is theta and z will be this, right, z will be this, one is that, another is this. So, this is the z. Right, the same is here true. Okay. If that be true, then here we have one unknown v theta, because we have been asked what is the velocity, right. So, that tangential velocity, if we want to find out, that is v theta, then this solution is good enough. 0 is equals to, we can take del del r, because here v theta is there, here also v theta is there, but here at least the equation is much, from here also you can solve. From here it is difficult, because obviously you will take the one where your solution is feasible. So, if we take this 0 del del r 1 by r del del r of r v theta, right. If we take this as the solving equation, then on first integration, as we found out earlier, 0 is equals to or this was okay, constant, integral constant, let us write here I is equals to 1 by r of del del r of r v theta, right. This was on first integration. So, which we could write on simplification as a r is equals to del del r of r v theta, right. Right. So, on second integration we can write then r v theta is equals to a r square by 2 plus b, right. A r square by 2 plus b. Up to this the solution is exactly identical. Now, where the change from the two problems, that is, again I am showing that this was already solved problem and this is the problem which we are now handling, right. So, here it was rotating, it is constant, here also it is rotating, this is constant, here the outer radius was kr, inner radius was r, here outer radius is r and inner radius is kr. This is the difference, right. So, up to this we have the same solution. Now, when we apply the boundary condition, the boundary condition is what? First boundary condition we can write, boundary condition 1 is that here, right. So, this is constant and this is rotating. So, this v theta is equals to 0 at r is equals to k r, right. This is boundary 1 and boundary condition 2 we can write v theta is equals to omega r, right, at r is equals to capital R, right. So, omega r at r is equals to capital R. So, if that be true, by applying the first boundary v theta is equals to 0 at r is equals to k r, right. We have these two, one a and b, okay. This was a and this is b. Now, if we put first boundary here, that r is equals to k r, v theta is equals to 0, that means this is 0, 0 is equals to a r square by 2, or in this case r is equals to 0. So, this also becomes 0, then b becomes equals to 0. Na? At r v theta is equals to 0, r is equals to k r, sorry, v theta is equals to 0 at r is equals to k r. So, v theta is 0, so this becomes 0 at r is equals to k r. So, this is becoming a k square r square by 2 plus b. This is say equation number 1, right. And the second equation is v theta is equals to omega r at r is equals to capital R. So, instead of this we write v theta is equals to omega r at r is equals to capital R. So, second one we can write r square, right, omega or omega r square is equals to a into r square divided by 2 plus b, right. So, from these two equations, by solving we can say that b becomes equals to 0, right. So, if we subtract this 2 minus 1, if we do 2 minus 1, then b becomes equals to 0, then r square omega, this is equals to a by 2. If we take common, then it becomes r square into r square minus k square r square, or if we take r square common, then omega is equals to, or r square omega is equals to a r square by 2 to 1 minus k square, right. So, from there we can also write this is that, okay, let us write here once again r square omega is equals to a r square by 2 into 1 minus k square, or a is equals to, this r square goes out. So, 2 omega over 1 minus k square, right. So, we had b is equals to 0, and we had the original equation v theta r v theta is equals to a r square by 2 plus b. In this equation, if we substitute the value of a and b, right, if we substitute the value of a and b, then r v theta is equals to, a is 2 omega over 1 minus k square divided by 2, right, plus b is equals to 0 into r square, right. Or we can write v theta is equals to, this r square and r goes out. So, 2 omega, this 2 and this 2 goes out, omega by omega r by 1 minus k square. So, v theta is rather is equals to omega by 1 minus k square into r, right. So, v theta is that. So, let us also check whether we have the same thing. Okay. Here in this, of course, we will try to, because this will be with you. So, boundary condition we change, v theta is to 0, if you remember that v theta is equals to 0, right, at r is equals to k r. So, let us substitute here V theta is equals to 0 at r is equals to k r. This is 1, and V theta is equals to, let us take it to that side, and V theta is equals to second omega r at r is equals to r, not omega k r, omega r at r is equals to r, right. So, if that be true, then by putting the first boundary, that is V theta is equals to 0 at r is equals to k r, we can write this was r v theta is a r square by 2 plus b, that was our integration, right. So, we write here that in this case we do not need this, right. So, we can write then that boundary condition V theta is 0 at r is equals to k r, and V theta is equals to omega r at r is equals to r. So, if we put this boundary, that is V theta is 0 at r is equals to k r. So, V theta is equals to 0 at r is equals to k r, then you get here this is k r square, right, k r square. And we can write it here if we have that thing, okay. So, it will be 2 square, right, and obviously this will bring down to normal, okay, k r square, this also has to come to normal only. So, this is subscript is out. So, k r square by 2, and this was b plus b only, right, plus b only. We are right. Boundary condition first one, if we have put here, so this is 0, right, and then this r is equals to k r is k r square, and oh no, let us keep that thing, this one with theta, then only, because we cannot put 0. So, it is a r by 2 plus b r. Here we have to apply, exactly, here we have to apply that v theta is equals to omega r at r is equals to r. So, from the first boundary, v theta is equals to 0 at r is equals to k r. If we put that, v theta is equals to 0. So, here it is k r square. Here it is then k r square. Okay. So, it is k r square by 2, right, plus here it is k b by k r, right, because r at we have first v theta is equals to 0 at r is equals to k r. So, b plus b by k r, and the second one was boundary condition was v theta is equals to omega r at r is equals to r. So, V theta is omega r at r is equals to r. So, in that case this will be A r by 2 plus this is B by r, right. So, that which we did a little here something difficult. Yeah. Now, let us rewrite here. So, we have 0 is equals to A k r square by 2 plus B by k r, and we also have omega r is equals to A r by 2 plus B by r, right. So, if we take instead of B, so B is equals to, from here we can write B is equals to minus A k r whole square by 2, right, divided by k r. So, this is k r minus A k r square by 2 k r, that is B. If we take this equation and if we substitute here, then omega r is equals to A r by 2 plus B is minus A k r square by 2 k r, right, 2 k r, and we also have 1 k r here, right. So, on simplification we can write that this is equals to, if A is common, r by 2 minus k square r square divided by k r into 2 k r, right. So, this k r, this k square r square goes out, then this becomes r by 2 minus half, right. So, this is equals to into A, of course, right. So, omega r is there, therefore, A is equals to omega r. Of course, this we can further simplify as if we take r common, right, 1 by 2 minus 1 by 2 r, right. From there, if we take out this r, we write again omega r is equals to A r into 1 by 2 minus 1 by 2 r, right. So, this r goes out. So, A is equals to omega by 2 r, and here it is 2 r minus 2, right, is equals to 2 omega r divided by 2 r minus 1. So, this goes out, it is omega r by r minus 1. So, if it is A, then B can be written as, from here we can write that omega r is equals to A r by 2 plus B by r. From there we can write, substituting A, omega r square by 2 into r minus 1 plus B by r, right. So, from there if we take this omega r, so B by r is equals to, B by r is equals to omega r minus omega r square by 2 r minus 1. So, if we take omega r common, then 1 minus 1 by 2 r minus 1, right. So, B is equals to omega r square into 1 minus 1 by 2 r minus 1, right. So, we know A, we know B, then we can substitute, and by doing that we get this, okay. We get this is the solution, okay. V theta is omega r into k r by r to r minus k r by k minus 1 by k, and of course, in all the cases we have missed that 1 k. Yes, we have missed that 1 k in these cases. So, this is the ultimate solution, which we get that V theta is equals to omega r into k r by r by k r by k minus 1 by k, and shear stress tau r theta is minus mu r del V theta del r del V theta by r del r of V theta by r plus 1 by r del V r del theta. So, that is minus mu 2 omega square into 1 minus r square into k square by 1 minus k square. So, you do the changes in the slide accordingly and convert it into this. Okay. Thank you.